In this module, you will learn to solve transportation problems using linear programming. In the previous modules, we learned to solve manufacturing problems and diet problems of linear programming. Let us now learn one more type of linear programming problems called transportation problems. In these problems, a transportation schedule is determined in order to find a way of transporting a product from factories situated at different locations to different marketplaces at the minimum cost. Let's take up one example. An aeroplane can carry a maximum of 200 passengers. A profit of 400 rupees is made on each executive class ticket and 300 rupees on each economy class ticket. The airline reserves at least 20 seats for executive class. However, at least 4 times as many passengers prefer to travel by economy class than by executive class. Determine how many tickets of each type must be sold in order to maximize the profit for the airline. Also, what is the maximum profit? Let the number of tickets of executive class and economy class be X and Y respectively. Hence, X and Y are greater than or equal to 0. The maximum number of passengers in the plane is 200. Hence, X plus Y is less than or equal to 200. The airline reserves at least 20 seats for executive class. It implies that X is greater than or equal to 20. However, at least 4 times as many passengers prefer to travel by economy class than by executive class. This gives us the inequality Y is greater than or equal to 4x. It is given that a profit of 400 rupees is made on each executive class ticket and 300 rupees on each economy class ticket. The total profit is 400x plus 300y. Hence, the objective function is z is equal to 400x plus 300y. To find the maximum profit, the objective function should be maximized using the constraints 1 to 4. Let us draw the graphs of the inequalities, treating them as equalities. The solution set of x is greater than or equal to 0, and y is greater than or equal to 0, is represented by the first quadrant. Draw the graph of x plus y is equal to 200 as the reference to get the solution of the inequality. Draw the graph of y is equal to 4x as the reference to get the solution of the inequality. Draw the graph of x is equal to 20 as the reference to get the solution of the inequality. The feasible region of the inequalities 1 to 4 is a bounded region. The coordinates of the corner points of the feasible region are A 20, 80, B 40, 160, and C 20, 180. Let us substitute the corner points in the objective function. The value of objective function is 32,000 at 20, 80. The value at 40, 160 is 64,000. And its value is 62,000 at 20, 180. The maximum value of the objective function is 64,000, which occurs at B 40, 160. Hence, 40 tickets of executive class and 160 tickets of economy class should be sold to get the maximum profit of 64,000 rupees. Let us solve one more transportation problem now. A factory is located at 2 places P and Q each. From these locations, a certain commodity is delivered to each depot situated at A, B, and C. The weekly requirements of depots A, B, and C are 5, 5, and 4 units, respectively, while the production capacities of the factories at P and Q are 8 and 6 units, respectively. The cost of transportation per unit is shown in the table. How many units should be transported from each factory to each depot in order that the transportation cost is minimum? Let us solve the problem now. Let X be the number of units transported from P to A, and Y be the number of units transported from P to B. Let us place the values in the table now. Now, X number of units are transported from P to A, and Y number of units are transported from P to B. Therefore, the number of units still left at P is 8 minus of X plus Y, which are to be transported to C. As the requirement at depot A is only 5 units, the number of units sent from Q to A is 5 minus X. Similarly, the requirement at depot B is only 5. Hence, the number of units sent from Q to B is 5 minus Y. The number of units left in depot Q is X plus Y minus 4. Let us form the inequalities using the data in the table. The inequalities are X greater than or equal to 0, Y is greater than or equal to 0, X is less than or equal to 5, Y is less than or equal to 5, X plus Y is less than or equal to 8, and X plus Y greater than or equal to 4. Using the table for cost and the number of units, and simplifying, we get total cost of transportation as X minus 7Y plus 190. To find the minimum cost of the transportation, we need to minimize the objective function Z, which is equal to X minus 7Y plus 190. Let us draw the graphs of the inequalities, treating them as equalities. Obviously, X is greater than or equal to 0, and Y is greater than or equal to 0 have the solution in the first quadrant. Draw the graph of X plus Y is equal to 8 as the reference to get the solution of the given inequality. Draw the graph of X plus Y is equal to 4 as the reference to get the solution of the given inequality. Draw the graph of X is equal to 5 as the reference to get the solution of the inequality. Draw the graph of Y is equal to 5 as the reference to show the solution of the inequality. The feasible region of the inequalities 1 to 5 is a bounded or a closed region. The coordinates of the corner points of the feasible region are A, 4, 0, B, 5, 0, C, 5, 3, D, 3, 5, E, 0, 5, and F, 0, 4. Let us substitute the corner points in the objective function. The value of objective function is 194, 195, 174, 158, 155, and 162 at the points 4, 0, 5, 0, 5, 3, 3, 5, 0, 5, and 0, 4 respectively. The minimum value of the objective function is 155, which occurs at e 0, 5. The values of x and y are 0 and 5 respectively. Substituting the values of x and y in the table, we get the required number of units to be transported from P and Q to A, B and C. So from the factory at P, we must transport 5 units to depot B and 3 to depot C, but none to depot A. Similarly, from the factory at Q, we must transport 5 units to depot A and 1 unit to depot C, but none to depot B. This will keep the transportation cost to the minimum.